This is fundamental problem 12-12. The sports car travels along a straight road such that its acceleration is described by the graph. Construct the position or the velocity versus position graph for the same time interval and specify the velocity of the car when s is equal to 10 meters and when s is equal to 15 meters. So we have the acceleration versus position graph here. Because acceleration is a function of position, we're going to be using equation 12.3, and this time we're going to use the equation just as it appears on the equation sheet. And we're going to integrate to find the velocity versus position. What we have to do here though, well, first of all, we have to look at the two different regions on the graph separately. So we're going to go from 0 to 10 and do the velocity versus position graph between 0 and 10, and then we're going to go between 10 and 15. So when I integrate this, I need to know how the acceleration is related to the position. Okay, if I put my integral signs in here, I can't pull the acceleration outside of the integral because the acceleration does depend on the position, but I can't integrate it unless I know how it depends on the position. So if we go to the graph here, I want to write acceleration as a function of position, and if we ignore the units, it's very easy to write this relationship because you will notice when position is 0, acceleration is also 0. When position is 10 meters, acceleration is 10 meters per second. So I can say the acceleration is equal to the position, but it looks kind of funny that way because the position does have units and the acceleration does have units. So if you wanted to find the slope doing the rise over the run, you would have 10 meters per second squared divided by 10 meters for the run, which would be 1. And then the meters cancel out and you just have 1 per second squared. So the units, it would be s times 1 per second squared, but then it just looks funny because this s is for seconds and this s is for position. So we'll just leave the units out, but know that acceleration and position do have different units, and the slope that you have here would take care of that, but the slope is 1, so you don't really see that in the equation. Okay, so I can just replace the acceleration with an s. So now I have s ds is equal to v dv. I'm going from 0 to 10 for position, so, but I don't want to put in the upper limit of integration as 10. If I did that, that would just give me the area under the curve. And if I was looking for the area under the curve, I really don't need to integrate to do that because I could just find the area under this curve by looking at the graph and doing the area of a triangle. So what I want from this is I want to get velocity as a function of position. So if I want it as a function of position, I can't go all the way to 10. I want to go to some arbitrary value of s. So my upper limit is just going to be s, and we do this whenever we want to find something as a function of position. Okay, and then what am I going to do for the lower limit of the velocity? Well, this is a little bit of a problem because we didn't do an acceleration versus position graph back in Physics 161, but we did look at acceleration versus time graphs. And if you have the acceleration versus time graph, you can integrate that, but can you tell me what the velocity is if I give you an acceleration versus time graph? You can only find the change in velocity. If you want to know what the velocity is at some given time, you have to know either the initial velocity or the velocity at some other point in time. They didn't give us the initial velocity here. Let's go back and look at the problem. It says the sports car is traveling along the road, and so, well, to be able to solve this problem, we have to assume something about the initial velocity. We're going to assume that the velocity when s is equal to 0 is also equal to 0. Okay, they really should have told us that, but they're not always good about doing that. And so we're going to make an assumption there. Okay, so when the position is equal to 0, we're assuming that the velocity is equal to 0, so the lower limit of integration is 0. My upper limit of integration is just v. That's how I'm going to find the velocity as a function of position. We've seen integrals like this earlier, so when you integrate s ds or v dv, you get 1/2 s squared on the left-hand side, you get 1/2 v squared on the right-hand side. When you plug in the limits of integration, you're going to get 0 when you plug in the lower limit of integration, so we have 1/2 s squared is equal to 1/2 v squared. So not only is the acceleration equal to s with the appropriate units thrown in there, the position is equal to v. I guess the only thing you would have to be careful about here is when you take the square root of both sides, if the position and the velocity are going to have the same signs or if they're going to have opposite signs. The acceleration is positive here, so if the velocity is 0 and the acceleration is positive, then when the car starts moving, it should have a positive velocity. So we say, and again, this should really be the position times 1 over a second in order for the units to work out. Okay, so that's for the first part of the graph. So let's start drawing our graph over here. So up until we get to 10 meters, the velocity and the position are the same value. Okay, we can say, because they asked us to find the velocity when s is equal to 10, so it would be equal to 10, but it's 10 meters per second, and the position is 10 meters. Okay, so now we're going to go from 10 to 15. I'm going to use this equation, but this is what I had when I go between 0 and 10. When I go between 10 and 15, I need to know what to use for the acceleration. It's not equal to, it doesn't depend on s anymore. It's always 10 meters per second squared if you're between 10 and 15. So we're going to use this equation, but now with a being equal to 10. So that's 10 ds is equal to the integral of v dv. And now the 10 can come outside the integral because now the acceleration is constant. It does not depend on the position. Okay, and this is only good between 10 and 15 meters. So the lower limit of integration is 10. My lower limit of integration for the velocity, that would be 10 also, because when the position is 10, the velocity is 10. My upper limit of integration is just going to be s because I want the velocity as a function of position. If I put the upper limit of integration in as 15 for the position, that would tell me what the velocity is. That would tell me what the area underneath the curve is between here and here, but it wouldn't give me the velocity as a function of position. So upper limit of integration there is v, and when I integrate 10 ds, I pull the 10 outside, I integrate here, I just get s, and then I evaluate from 10 to s. Here this is v dv as we've seen before, this is 1/2 v squared, and then I'm evaluating from 10 to v. So I can go ahead and plug in the limits of integration. So this is 10 times s minus 10, and this is 1/2 v squared minus 10 squared, which is 100. I want to solve this for v, so this would be 10s minus 100, then multiply by 2. This is 100, and this is minus 100, so bring that over to the other side. And you have plus 100, and then take the square root. So this is 20s. This 2 times 100, that would be 200. It's negative, so it's negative 200 plus 100, which is minus 100. I forgot there. That should be plus or minus. But I know it has to be positive because we're going from 10 to 15. When I'm at 10 meters, my velocity has to be 10 meters per second, which means we have to choose the positive value there. Okay, so then I need to finish drawing the graph. The slopes have to match at this point here, so not only does the velocity when you're coming in from this side have to go to 10, so they're at the same, so it's continuous, but the slopes are also continuous, and that would look something like this. Here's a tip for you when you're doing homework. If you can't make your graph look exactly like what it should look like, just give me the equation so I know what you're trying to graph. So this is 20s minus 100, and then do your best. Okay, so your graph doesn't have to be perfect, but if you put the equation in, I know what you were trying to draw, so that's helpful. Okay, so then to conclude, we have to find the velocity when s is equal to 15 meters. Okay, that's easy. The velocity when s is equal to 15 meters, we just plug 15 in here, so it's 20 times 15 minus 100, and that gives us, you can plug this into your calculator, you should get 14.1, and let's stick some units in there. Okay, so we have our graph, and we have the velocity when s is equal to 15, and I feel like somewhere we should have the velocity when s is equal to 10, but maybe we didn't write it down, so let's just put it here, is equal to 10 meters per second. Okay, and that concludes fundamental problem 12.